The first speaker of this session is Professor Michael Griffin. He did his PhD from Emory University under Professor K. Nono. He was a postdoc at University of Cologne and Princeton University. Currently, he is a senior lecturer at Vanderbilt University. And the title of his talk is Mass Operators in Integral Weight, Key Definition and Equations. Thank you.
Thank you so much. I'm very excited to be here today, and I'd like to thank the organizers for the opportunity to come here and present these series of talks with Nick. And also thank you, Nick, for that first lecture. It set the stage so well for what we're going to continue with. As with Nick's lecture, we're continuing more or less working through a lot of the topics in this book. We're going to rely a lot on the notation in this book, even in a couple of circumstances where I might prefer some other notation. I'm going to try to adhere closely to their notation. So if you have that book, if you are referencing that, trying to learn more about harmonic Maass forms, hopefully everything that we're talking about will line up with what's in the book. There are a few cases where, especially in terms of like proofs or something, I might do something a little bit different than what they're doing, but I try to keep it at least consistent with everything that's in there. I'm also going to be experimenting a little bit with our format today. I'm going to use the slides right here just to present some key identities and some equations that I'm going to use in my talk, but everything else is going to be here on the board. And we'll see how that goes for today. But as you can see, I don't have very many slides here. This is mostly going to be on the board, and we'll leave the format very similar to Nick's lecture, where I invite you to ask questions as we're going through. Please treat this as a classroom experience. If I say something that's not quite clear or you have any questions, please ask me. So we will start by setting up. We'll just remind ourselves of these Maass operators that we ended with Nick. So we have the raising operator, the lowering operator, the Xi operator, and they have these relations with the Laplacian delta K. Okay, so this is kind of our background, of our starting point coming from Nick's lecture. A couple of things that we are doing in my lecture, different from Nick's lecture. We are going to assume that the weight is all integral. Okay, and I'm also more or less going to always assume that we're dealing with level 1 forms. So that means gamma is equal to SL2Z. Okay, there are a few places where I'll point out how some of the formulas will change for higher level. But for the most part, most of the things that I describe are going to be pretty similar across the board. Just for simplicity, I think it's easier just to kind of focus on this situation. Okay? And so because of that, I'm going to kind of drop gamma from my notation. Okay. So with that, just kind of an overview of the operators that we're going to be focusing on today, we are going to look at something called the Bowles operator, which we're going to build from these Maass operators right here. And we're going to study this a little bit. It's going to help us understand some of the structure of our spaces of harmonic Maass forms. We're also going to study the Petersson inner product. And then we're going to study the Bruinier and Funke pairing. Okay. And altogether, these are going to give us, we're going to be able to use this to give a better idea of the structure of our spaces of harmonic Maass forms, how they kind of decompose into important subspaces, and how we can use them to build harmonic Maass forms in different ways that we might want. Okay. So first thing we need to do is to be able to build a Bowles operator. To get to that, we need to understand a little bit more about this raising operator. Okay? So the raising operator, some of the facts that we want about the raising operator. There we go. So our raising operator, okay, we have it there. I can rewrite this in a couple of different ways. This first way that I might write this, where am I at? There we go. So this is, I can write this as just I times the partial with respect to u plus the partial with respect to v plus k over v. Okay, now this is just splitting up this partial with respect to tau. Okay, Nick wrote this, but again, remember this is 1/2 times the partial with respect to u minus I partial with respect to v. Okay. Oh, did I? What's that? Oh, yes, yeah. This one right there. Is that what I missed? No, that's not what I missed. That's what it, yeah, okay, there we go. Good. Okay, so we've got this. And this kind of illustrates why we normalize the raising operator the way that we do. Our attention with a lot of these Maass operators very much is on the v coordinate, okay? So this makes this, the piece that respects the v coordinate is just as it is, just the partial with respect to v plus some other stuff, okay? Now, another thing that we might care about with the raising operator is its relation with this operator d, okay? Professor Murthy talked about this. This is one that's very interesting. It's studied quite a bit when you're dealing with modular forms with integer coefficients, okay? Usually, this is described in terms of q. So q d dq, you want to write this in terms of tau. This is the same thing as 1 over 2 pi I partial with respect to tau, okay? As you can see, that's closely related to our raising operator, but it has this slight difference, okay? Our Rk here is equal to our differential operator d here, times minus 4 pi, and then, of course, plus that non-holomorphic component there, okay? Now, as Nick mentioned, the raising operator preserves modularity, okay? It changes the weight, but it preserves modularity, whereas this d differential, the holomorphic differential, does not really preserve modularity. We're very close to it, but not quite, okay? And so this gives us this connection between these sort of almost modular things and these true modular things that are now non-holomorphic, okay? And this is this connection that gives us quasi-modular forms arising out of our standard modular forms, okay? Now, a couple of notes, some other properties of the raising operator that we want to talk about, okay? Nick, of course, mentioned that the weight changes. So if I take a function f and I act on it by some matrix gamma with a weight k slash operator, okay? This is the same thing as taking the raising of f first and then acting on it by a k plus 2 slash operator, okay? That's the first thing. The next note is what happens with the Laplacian, okay? As Nick mentioned, this changes the eigenvalue. We want to be a little bit more precise about that because we want to use this a little bit later. But it turns out that if I take the raising of f, and so now it's weight k plus 2, and I apply the Laplacian of weight k plus 2 to this thing, this is now going to act like the raising of f, okay? It passes through here, but there's an extra piece here, plus k times the raising of f, okay? And so this is really useful for us if f is an eigenfunction for the Laplacian, okay? if delta k of f is equal to lambda times f, then what happens over here, this becomes delta of k plus 2 of the raising of f is going to turn into lambda plus k times the raising of f. Okay? So it changes this eigenvalue by the weight. Okay? And that's all that happens there. Okay? The raising operator also has a product rule that at some point in this talk, depending on time, might show up in a proof. And otherwise, we might have to skip that proof, and so we won't see that. But I'll at least give you the product rule in case it shows up. But let me write it this way. So if F is weight K and G is weight L, okay, then if I take the product of F and G and I want to apply the raising operator to that, so that is going to be weight K plus L. Okay. This turns into the weight K raising operator on F times G plus F times the weight L raising operator on G. Okay. Yes?
So functions more general than the harmonic mass function. Not zero, but eigenvalues.
Yes, yes. So all I need here is that these are real analytic functions. And yeah, so at this point, if I have this Maas eigenvalue, yeah, thank you for that. Yes, yeah. So this is all this is dealing with at this point is just real analytic functions that behave in some way with our modular transformation, and yeah, some kind of nice properties here with the Laplacian. Okay, let's see. Good. Now, the next thing that we want with this is what happens when we apply the raising operator multiple times. We iterate the raising operator, okay? So we don't, if I have to iterate the raising operator, of course, I'm changing the weight each time. So I go from K plus 2, and so on, okay? Instead of writing all of this, I'm just going to call this RK to the N, okay? And this is going to be just this iteration where I take N copies of the raising operator where the weight changes the appropriate amount each time. So this is going to go over to R to the K plus 2 times N minus 1. Okay? And so we just apply this raising operator this many times. Now it turns out we get sort of a complicated formula for this expression. Let's see. Need to, the computer itself went to sleep. Okay, well, I will write out the formula here. This formula isn't too terrible. But what we end up having here is that this turns into a summation from R equals 0 to N choose R. Then I'm going to have a symbol here that's I'll define in just a moment. This is called a Pockhammer symbol. This is going to be K plus R sub N minus R. Okay. Then I'm going to have a 1 over V to the N minus R. And then we're going to have a 2i partial with respect to tau to the rth power. Okay. Now this piece right here, of course, if I'm interested in rewriting this in terms of the D operator, this part right here is just the same thing as minus 4 pi D raised to the rth power. Okay. Now, I'm not going to prove this. I'm going to leave this as an exercise. It's not terribly difficult. It's just using the chain rule and induction. But it is an exercise that is well worth doing for anybody who is working in harmonic Maass forms. Okay. The sort of identities and rearranging, there's a rearrangement of terms that you should pay attention to. Again, not terribly difficult, but it's the sort of thing that happens a lot in these formulas when you're dealing with harmonic Maass forms and using things like this raising operator. Okay. Okay. So that is our iterated raising operator. This leads us to Bool's identity. And through Bool's identity, the operator that we're going to call Bool's operator. Okay. And Bool's identity is simply this. So if I take this iterated raising operator, okay, I'm going to make some specific choices here. We're going to take the raising operator from weight 2 minus k. Need to stand back just a bit. There we go. And this is assuming that k is positive, let's say at least greater than or equal to 2. Okay. So this part right down here, this is going to be a non-positive integer. Okay. And I raise this k minus 1 times. Okay. Okay. So I'm making a specific choice in the weight and how many times I'm iterating this. Okay. Then it turns out that this is equal to minus 4 pi times our d operator raised to the k minus 1 times. Okay. So this is an important identity because, again, this raising operator has this non-holomorphic contribution, okay, this v here in the denominator. Okay, so we've got these non-holomorphic pieces times this holomorphic derivative. And what Bool's identity is saying is that all of the terms where this exponent is non-zero disappear in the identity. Okay? So why does that happen? Yes, and yeah, we'll talk a little bit more about how that happens more generally, but the first thing that I want to pay attention to is what happens to weakly holomorphic modular forms. This is an operator that will take something of weight 2 minus k. So the Bool operator, let me focus on that really quick. So the Bool operator is just going to be that dk minus 1. Okay. If I act on a weakly holomorphic modular form of weight 2 minus k, my result will be something weakly holomorphic of weight k. And then we'll see in just a moment how this works on our more general spaces. But yeah, so dk minus 1 will take the space of m2 minus k bang, and the result is in mk. Okay. Now this is not at all surjective, okay, but the image is in these weakly holomorphic forms. Okay. Now, why does Bool's identity hold? I didn't define my my Pockhammer symbol. I got distracted there. The Pockhammer symbol. Let me just do this. So x sub m is going to equal this product x times x plus 1, and so on until I get to x plus m minus 1. Okay? This is often called a rising factorial, right? We're increasing these terms, and this m here is just telling me how many terms in this product do I see. Okay? So we certainly need that for this to even make sense at all. Okay? But this is our That's our Pockhammer symbol. Okay. Now what's happening here is this formula. Let's actually write this out in the case we're going from 2 minus k to k. That formula becomes the sum from r equals 0 up to k minus 1. K minus 1, choose r. And then we get this Pockhammer symbol here. 2 minus k plus r up to k minus 1 minus r. And then from here we get our 1 over v to the k minus 1 minus r minus 4 pi d raised to the rth power. Okay. And what's happening here is this Pockhammer symbol right here. Okay. Our initial terms here, we start at 2 minus k plus r, and we go all the way up, and that final term, okay, we add those together and subtract 1. That final term in this Pockhammer expression is a 0. Okay? So every single one of those is going to vanish, except when this index right here is 0. When that index is 0, our Pockhammer symbol is an empty product. Okay? And so that's all that's left over. Okay? We only have that term r equals k minus 1. That's the only piece that's left over. Okay? So Bool's identity follows very nicely just from this formula. Okay? Any questions on that at that point? Okay. Yes? Oh, sure. We'll delve all into that in just a few minutes. Yes. That's one of the big motivating points of understanding this Bool operator. Okay, we have that this image. How does this span out with everything else that we have here? Okay, so we have Bool's identity. Let me just turn this here. Okay, so there's our formula for the iterated raising operator, Bool's identity. Okay, and oh yeah, I had one other way I wanted to describe Bool's identity here for you. And this uses the way that the iterated raising operator changes the Maas eigenvalue. Okay. Oh, I just erased this. That's fine. So if I'm going from weight 2 minus k up to k, again, remember this is a raising operator where we go from 2 minus k dot 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 all the way up until we get to a raising of k minus 2. Okay. Now again, remember if delta of f, let's say 2 minus k, if this is equal to lambda of f, so we're starting with a function with a Maas eigenvalue, what happens as we apply this raising operator over and over again? Okay. Well, this one is going to add that weight 2 minus k. The next one is going to add 4 minus k, and so on. I'm going to get out here to this end. This one right here before the last is going to add a k minus 4. This next one is going to add a k minus 2. Okay? So at the end of the day, after I've applied all of these raising operators, what's happened to my eigenvalue? All of those additions directly cancel each other out. I'm back to the same eigenvalue. In particular, if I start with something harmonic, I have to end up with something harmonic. So dk minus 1 is going to take anything in my space of harmonic Maas forms. In fact, I'll use the H-bang. And the result has to be a harmonic Maas form of weight k. And I guess I should leave my bang on here. We'll make this a little bit tighter here in just a moment. Okay. So next step is another exercise, because I don't really want to go through details on the board, but it really is just a calculation. So exercise, apply dk minus 1 to the incomplete gamma function k minus 1, comma, minus 4 pi n v, where n does not equal 0, and you should find that that equals 0. Okay. So Bool's operator exactly kills the non-holomorphic part of a harmonic Maass form, except for one term. Does anybody remember what when Nick wrote out these coefficients for the harmonic Maass forms, do you remember the kind of the n equals 0 term for the non-holomorphic part? Anybody remember what that looked like? Yeah, we had a v to the k minus 1. Okay, so there'll be some constant here times v to the k minus 1. What happens when you apply dk minus 1 to this? This is just going to turn into, well, it'll turn into a constant. Let's see, did I figure out what that is in my notes? Nope, I didn't write down what it is in the notes. Okay. But this is our exercise. Okay, figure out what this constant is, show that that goes to 0. Okay. Again, not a terribly difficult calculation, but just a calculation to do. Yeah.
So there's supposed to be a q to the n.
Oh, there is. Yes, and that is important. It doesn't work right without the q to the n. It does not work right. Good. Okay, is that clear? Okay. So, what does that tell us? How can I modify this expression right here, given the information we just have? It turns out that I'm not going to just general harmonic Maass forms here. I am actually going to MK Bang. Okay. Does that make sense? Is that clear to everybody? Okay. So this is Bool's operator. Okay. Now, let me write out a couple of things in just a moment. I'm going to write out a diagram that kind of shows some pieces, how they come together. Right now, really quickly, I just want to point out that this looks very similar to the expressions that Nick gave us for the Xi operator, right? Okay. In a lot of ways, Bool's operator is dual to the Xi operator. That only makes sense, though, when we're dealing with integral weight. Okay. There's a very rich theory of half-integral weight modular forms. The Xi operator makes sense there. Bool's operator does not. There's not even a modification of it that really makes sense or really works the way that we have it here in half-integral weight. So this really is something that comes here from integral weight. Okay. Okay. So given that, let me draw a diagram. We're going to reference a little bit through the rest of my talk. Okay. So on one side here, I'm going to look at H2 minus K bang. And over here, we're going to look at, oh, no, I do actually want to look at HK bang. No. I don't. I really want to look at just MK bang. It turns out there's not a lot written about HK bang in the positive weight space. There's a lot of the things that we talk about here work just as fine in that case. We actually don't have a lot written there. So I am going to, in positive weight, I'm pretty exclusively going to be talking about the weakly holomorphic forms. Okay? Now it turns out I'm going to write these. I'm going to draw these spaces like long sequences, sort of. There really is a natural way to kind of index these by the integers, at least for the harmonic Maass forms for SL2Z. Okay? For higher level, you have to maybe include some kind of indexing for each cusp, but for the moment, we're just going to focus on SL2Z. There's a nice way to index everything in terms of the integers. Over here in MK bang, I'm going to draw some nice spaces here. Up here, this is going to be SK. These are our cusp forms. Okay? Our indexing only goes so far because this is a finite dimensional space. Okay? After a certain point, if I try to index them the same way that I'm doing everything over here, I'm just going to get forms that are 0, or at least things with linear combinations of these things down here. Okay? So if I try to reduce anything in any logical way, I get 0 for those higher indexes. Right here in the middle, there's a one-dimensional space, the Eisenstein series. I'm sorry, that's going to be too small. Be able to read. Okay. And then down here, okay, of course, we have things that are more general weakly holomorphic modular forms, but if I really want to separate them from the Cuss forms in the Eisenstein series, I'm going to want to separate them in a certain way. I'm going to get something called SK perp. Okay? And we will explain this a little bit more in a minute, but these are things that are orthogonal to our holomorphic forms with respect to the Petersson inner product. And we'll talk more about that when we get there. Okay? But that's sort of a nice canonical, in some sense, way to separate these forms from these forms. Okay? Now, if we come back over here in our weakly holomorphic forms, or sorry, our harmonic Maass forms of negative weight, okay, somewhere down here, we have to have our index. We have to have a certain size of pole for us to be able to actually find weakly holomorphic modular forms. Okay? It turns out that this sort of there's sort of a space here in between. Okay? Up here, this is going to be our space H2 minus K. Okay? I can take an index all the way from 1 to onward. The space here in the middle, this has codimension same as the Cuss forms. Okay? Really what I'm looking at here is these are the forms that map up to my Cuss forms under C2 minus K. Okay? Whereas everything down here under C minus 2 minus K are getting mapped to 0. Okay? Weakly holomorphic get mapped to 0. This set right here is getting mapped over here to my Cuss forms. Okay? Here in the middle, there is a non-holomorphic Eisenstein series. I'll talk a little bit more about that probably next time. But there is a non-holomorphic Eisenstein series here in the middle. Okay. And then I've got some things up here. Okay. I'll draw another line over here. Let's see, things up here. These are the space that, Nick, you called H2 minus K sharp. I don't know whether those include the Eisenstein series or not. I think the definition you wrote would include it, but it depends on whether or not you want to exclude polynomial growth or. Okay, so these might include this Eisenstein series or might not. It sort of depends on how we set up our definition. The fact is there's not a whole lot written about this non-homomorphic Eisenstein series down here in this setting. Usually when we were thinking about the Eisenstein series, we talk about it kind of all together. There's not a lot that's interesting about this that we can't learn just from the standard real analytic Eisenstein series. Okay? So we'll talk a little bit more about that tomorrow. Okay? But anyway, this is our space H2 minus K sharp and H2 minus K. Okay, so this is our setup just using the C operator. Okay. Oh, and I guess I should, just to fill this in, of course, right down here, this non-homomorphic Eisenstein series maps over the Eisenstein series using C. These ones up here, well, sort of everything up here maps down here to SK. Okay. That's all using the C operator. The Bowles operator goes straight across. Okay. So right through here, okay, I've got dk minus 1. The image of the Eisenstein series under dk minus 1 is still going to be Eisenstein. Okay. Down here, again, we'll prove this in just a moment using, once we talk about the Petersson inner product. But But everything down here maps over here to SK perp. Okay. In fact, I can make a little stronger let me break this up in a little stronger way. Right down here, the image under dk minus 1 of my weakly holomorphic modular forms, these are forms that sometimes we call exact. Okay. We'll make use of this in a minute, but if you study things like de Rham cohomology or anything like that, these are the exact forms that you would be interested in. Okay, studying your modular forms modulo the exact forms. Okay. And then, yes, up here, we also have this space, our purely non-holomorphic modular forms somewhere up here are going to map over to 0. Somewhere in the middle, we've got forms that map over to our cusp forms. Okay. I guess I should write that up here. We do have purely non-holomorphic forms as well. Okay. So we have this diagram with these spaces that map straight across using dk minus 1 and sort of twisted using like C operator. Yeah.
Dotted ones.
Yes, dotted is Xi, the blue straight across is dk minus 1. Okay. Does that make sense? Any other questions with this? Okay. Now there's definitely things that I've written up here that I'm going to want to explain a little bit more fully in just a minute. Okay. But this is sort of the diagram that we're going to try to understand, okay, try to fill in our details for, understand the structure of our harmonic Maass forms. Let's see where we're at. Okay, doing good on time. Okay, so, yes. Yes, subspaces. And each one of these bands correspond to actual subspaces within our larger space. Okay, SK perp is a subspace. The exact forms are a subspace of that. Okay, our cusp forms are a subspace of our holomorphic forms. But yeah, everything here is set up to be a subspace of our larger. Sorry, what decomposition? Yeah, so specifically, so over here from MK Bang, I mean, we've got our cusp forms and our Eisenstein series. Hopefully you believe that that's canonical, okay? And that is a canonical subspace there of everything else, okay? We make this division here from our exact forms, okay? And everything over here kind of comes from what is the image, or what's the pre-image of something over here, okay? But yeah, everything here really is canonical in a lot of interesting senses. If you want to study things like de Rham cohomology, a lot of times this is what you're looking at, okay? I mean, you're looking at cosets, but you can always focus on something in this space, okay? You're looking at your holomorphic forms and so on. Okay? And a lot of our interest in the harmonic Maass forms comes down to sort of corresponding subspaces in the integer or the positive weight. Good. Any other questions there? Okay. Now, really quickly, I want to get to the Petersson inner product in just a moment, but there is an interesting operator we need before we get there. This is something called the flipping operator. And this operator kind of helps us understand the symmetry from our negative index to positive index forms on this side. Okay. Flipping operator. Okay. And this flipping operator, did that die? Okay. That's fine. The definition is pretty simple. The formula for the coefficients gets a little more complicated, which is one of the reasons I wanted to have it up on the presentation, but I can write this, it's fine. So I'll use a curly F here, curly FK, and this is defined to be minus V to the minus K over minus K factorial rk to the minus k of f, and then conjugate it. Okay. Now this makes sense. This only makes sense with k negative. Okay. Now everything else in my talk, I've tried to keep k positive and use 2 minus k for the negative weight. This is the way it's written in the book. I copied it from the book. I maybe should have still made that change just for consistency with everything else. But this is our definition. Just remember, k has to be negative or this doesn't make sense. I guess less than or equal to 0. Okay. Now what happens here is if we assume that f is in HK bang, then the flipping of f is also in HK bang. Okay, it's an involution on this space. Oh, guess I should write that as the second one. So it's an involution on the space. So if I apply the flipping operator twice, this just comes back to itself. Okay? So it's normalized exactly right. So we get back to itself. I'm going to properties here. I'm going to go a little bit out of order here with our properties, but I'm going to assume, so if I have a Fourier expansion for f, so I'm going to write this out the same way that Nick did. So if f of tau is equal to, let's do our sum for n bigger than minus infinity, we'll say c plus of n q to the n, plus, now I've got our non-holomorphic constant, so c minus of 0, b to the k minus 1, and then we're going to add the non-holomorphic sum here, n less than infinity and not equal to 0. Right, c minus of n. We'll have our expression with the incomplete gamma function, 1 minus k minus 4 pi nv q to the n. Okay. Then the flipping operator of f, I guess I should give myself a little more space here, is basically going to exchange our coefficients for the holomorphic and the non-holomorphic part. Okay, so we'll have this sum for n bigger than minus infinity and not equal to 0. We'll have our c minus of negative n, and I'm going to conjugate it q to the n. Okay. I'll have my sum n less than infinity and not equal to 0. I'll have this gamma expression. I won't write, let's see. This gamma expression, q to the n here. And then out front, I'm going to have my c plus of minus n conjugate. Okay. But I need to decorate these just a little bit. This is going to be a minus k factorial here. On this side, I'm going to have a minus k factorial here. Okay. And so you can see these, the minus and the pluses are basically swapping places. Now that doesn't happen with the 0 coefficients. They're still going to be conjugated, but we're going to get a minus c plus of 0 conjugate. That stays there as the constant without the v term. And then we're going to have a minus c minus of 0 conjugate b to the k minus 1. Okay. So those terms there, they just become conjugates of each other. These ones over here, coefficients are conjugated. They swap holomorphic to non-holomorphic. And then we get this weighting, one by a minus k factorial, the other divided by minus k factorial. Okay. Does that make sense? Any questions there? Yeah. Yes. Yeah, this right here is going to look just like this one up here. Yes. Yes. It's going to be the one that makes sense. Let's see. It should be. Yeah, it's got to be the same. So n is, so I wrote these as sums with n generally negative here. So this has to be, it has to just be a minus 4 pi nv. Yeah. So this term right here looks exactly like this term. Okay. So this is the expression I didn't actually want to write on the chalkboard. Hopefully I wrote it clear enough that people can copy it if you want to, but a better source is just to read it from the book. Okay. But this is probably why we mostly care about the flipping operator. It gives us this sort of way of exchanging these spaces. Okay, it maps this space here up here or back. Okay, this part down here are weakly holomorphic ones. It maps up to the purely non-holomorphic, and vice versa. Okay, flipping operator gives us this way of understanding everything up here from these ones down here, and this is one reason why we don't often spend a lot of time studying this H2 minus K sharp, because we can learn almost everything we want about this space from learning about our space down here. And that's not quite true in the case of half integer weight. And I think Nick is going to end up talking a little bit more about that later. Half integer weight, these don't have that same nice duality where you can go back and forth between them. Okay, let's see. Okay, good. Let me write a couple more properties of this flipping operator that we want to use. We have a couple of really nice properties here. So if I apply the Xi operator to the flipping operator of f, okay, it turns out that we get a multiple of dk minus 1 of f. Okay, the multiple is 4 pi to the 1 minus k over minus k factorial. Notice if you rewrote this in terms of the raising operator instead of using r instead of d, this 4 pi would go away. Okay. Let me see if I can get this last one in here. Yes. Oh, you're right. You're right. K is negative. We should be like that. Thank you. And then the last one that I want to do here is again d1 minus k times our flipping operator of f. Okay. This is going to equal, it's just going to be the inverse here, minus k factorial over 4 pi to the 1 minus k times ck of f. Okay. So this is one of the really nice parts about the flipping operator. You can really see how our bowl operator is dual to our Xi operator. It just really illustrates that point pretty clearly. Okay. Good. Any questions there? Okay. That is all I wanted to talk about the flipping operator. What time is it? 3:19? Okay, good. Okay, let's move from there. I'm going to leave the diagram up. I want to come back to that in a couple points here. I've got enough time here. I should be able to talk about the regularized inner product. We may not get to the pairing. We'll leave that for next time, but that'll be fine. That'll lead right into a lot of our discussion about the examples for next time. The Petersson inner product, the standard Petersson inner product is just an inner product on our spaces. This will take something holomorphic of weight k and a cusp form of weight k, and its image is some kind of constant, okay? And this is defined I take f comma g, this inner product is defined to be the integral over a fundamental domain for whatever group we're working with, okay, of f of tau, g of tau bar, v to the k, du dv divided by v squared. Okay. When we split this up, we have our v squared with the du dv, just so that this is an invariant measure on our space. Okay. And this is, again, our fundamental domain. So we look at the upper half plane and you mod out by the action of SL2Z. I expect a lot of people in this room, hopefully most of you have seen this, but you can always relate this basically to a fundamental domain that looks like this, where this is the unit circle. Okay, we want to be outside the unit circle, and then real part between -1/2 and 1/2. Okay, that's a standard choice for a fundamental domain, but any choice for a fundamental domain will work for our integration here. Okay, does this make sense? Okay. So this is our usual choice for Petersson inner product. We would like to regularize this so that this makes sense for a slightly larger set of functions. Okay. And the way that we're going to do this, we're going to define it this way. I'm going to just write regularized, so reg for regularized up here. There's a good chance I will forget to continue writing regularized, so just assume I'm using whichever one is necessary here. But this is going to go from all of mk bang cross sk to C. And all we're going to do here is we're going to start by truncating our fundamental domain. Okay, so ft here. Let me finish out writing the rest of this. So the rest of this looks exactly the same as before, v to the k minus 2 du dv, but we're going to truncate our fundamental domain. So this is going to look like this, and then we just chop it off up here at height t. Okay? And then we are going to take the limit as t goes to infinity. Okay? Now, we could truncate our fundamental domain in a lot of ways. All we really need, in a topological sense, I need this to be a limit of compact sets that converge to my full fundamental domain. But this is a really nice choice because it makes our integrals really nice to work with. Being able to turn this into an integral straight across in the x direction makes this very nice for actual calculations. Okay. And once again, this converges, allowing f to be, allowing that to have exponential growth. Okay. Just as long as g here, g still has to be a cusp form. Does that make sense? Good. Okay. Now there are some stronger versions of the regularization. I'm not going to go into those, but sometimes they're useful if you're doing things like theta lifts or something else where you're trying to do sort of an inner product with a more exotic kind of real analytic modular form. Just understand those do exist. If you're working with something that you want an inner product and this doesn't converge, there probably is a stronger version of it that might. Okay. Now, this is the result that we want to make sense with our diagram here. Okay. So claim. So if f is in H2 minus k, Okay, so I'm starting with a harmonic Maass form, weight 2 minus k. And G is any cuss form of weight k, then our inner product of d k minus 1 of f comma g is equal to 0. Okay, this is where we get this description for SK bang. Okay, or sorry, SK perp. This is supposed to be our set. Everything down here that is orthogonal to our cuss forms, and then, well, I guess the one other condition we're going to put here for SK perp is that we have a constant term of 0 so that we can exclude all of our Eisenstein series. Okay, but this is sort of our defining feature here, is that everything that's under the image of our Bull operator is orthogonal to our cuss forms. Okay. Now, the proof of this is, it's not terribly difficult. It is kind of annoying. It really is an application of Stokes' theorem. Okay. And we're able to use Stokes' theorem because we've got an integral of a derivative. Okay. Stokes' theorem allows us to change this, okay, step backward one step from the derivative. That'll turn this two-dimensional integral into a contour integral, okay? And well, you go through those steps and you get that this has to end up being 0, okay? Again, not terribly difficult, but just enough. I don't really want to go through the details. And so I will, of course, leave that as an exercise for you. Just make sure to use Stokes' theorem. You will also need to use some facts about the Fourier expansions of f and g. Yes? Yeah. Yes. Yes. So up here I've got my purely non-holomorphic forms are mapping to 0. Yeah, so the solid one, dk minus 1 goes directly across. C is going at this diagonal. Yes, so this is going to our orthogonal space. Yeah, and the things that are going to 0 either are purely non-holomorphic, are going to 0 by dk minus 1, or our weakly holomorphic ones are going to 0 by C. Yes. Okay, so we have sort of ending here on this point here. This claim, I'm telling you, this is an exercise using Stokes' theorem, but I think we'll probably end on that. And that tells us just this image, dk minus 1 gives us our orthogonal forms here. Okay? And we'll fill in a couple more details about some of these spaces that I've kind of left open next time. We'll talk about the non-holomorphic Eisenstein series, okay? And then we'll be able to use the Bruinier and Funke pairing that's based on this inner product to get a few more interesting results about these spaces. So we'll leave that till next time.
Any question?
Yeah. Sorry, say that again. This one right here? Well, so this one down here, we're truncating our fundamental domain. So this will be finite in this case, as long as, yeah, we're working with something in, oh, I said, yeah, as long as we're working with something in MK bang and SK, this will be finite, and the limit does exist here. Again, this has to be modular, this has to be a cuss form. If that's not a cuss form, then we have some issues. I mean, we could swap the places of f and g, but we need at least one of them to be a cuss form or some similar result there. Yeah, but otherwise then it will converge.
Any other question?
Yeah. If F has a non-holomorphic part? I believe that's probably true, but I'm not, I have never worked with this integral with a non-holomorphic part here. So the thing that I will want to do, and we'll talk about next time, is, well, yeah, so what exactly happens here? Well, let's see. What am I trying to say? I don't know what I'm trying to say. Well, that all comes back to this. No, I don't actually know what happens here with the non-holomorphic part. I've never worked through that integral. They don't talk about that in the book. But I suspect that things can go very wrong.
So the definition of solid space is
Yes, exactly. Yeah, so I should probably write this somewhere. So SK perp is equal to the set of forms of F in MK bang such that F comma G is equal to 0 for all G in SK, and then also the constant term of F is equal to 0. That's all it is. And that part just gets rid of our Eisenstein component.
Any other question? No question? So let us thank this.